Hey everybody, it's Rob. We're back. We're going to do something a little different today. Today we're going to walk through writing a buffer overflow exploit for a Windows 32-bit application, a vulnerable app. There's a couple of things that we need to do to get ready to do this. So you have your Kali VM. You're going to need a Windows 10 VM on the same network as your Kali machine. I downloaded Windows 10. I think it was released 1903. I got it from archive.org, and there's a well-known volume license key out there you can find for yourself that'll allow you to install it. Now, you won't be able to activate it or anything with that key, but you don't need to. So, now, a few other things we're going to need are we're going to need a vulnerable app. So I have a link here to my GitHub that has several of these. We're going to be doing oscp.zip. So it's an application that has 10 buffer overflows you can practice on. We're going to be doing overflow 2. You're going to need a fuzzer. Now you can either write one or you can use one that I've provided here in my GitHub repository. Basically, all it is a loop that keeps sending increasingly larger strings of data to the application and then basically crashes it. And it gives you a roundabout estimate of where the program crashes as far as the amount of bytes sent. We'll need to do a little bit more work to get the exact offset that tells us when the application crashes, but the fuzzer will give us a roundabout number that we can start with. On the Windows machine, you are going to need to download Immunity Debugger. It's a debugging program. It's kind of old, but it works well. And for our purposes, it's going to be perfect. And with Immunity Debugger, we're going to need a tool called Mona. It is a Python program. And you can just follow the instructions here on where to put it. You need basically just put it in the PyCommands folder in the Immunity Debugger application folder. And then you need to make sure your Windows machine has Python 2.7 installed. I believe there's a link here somewhere for that. So you don't have to worry about it. If you just follow all the instructions in this GitHub repository, you'll be fine. So we're going to write the exploit together. We're going to walk through this together. This video is going to be kind of long, so if you want to watch it on 1.5 speed for the first time, and then maybe just go back and review the parts where you have problems, that would probably work. So without further ado, I have my Kali VM spun up, and I have my Windows 10 VM spun up. You can see I have Immunity Debugger on here. The first thing that we need to do is we need to get the application that we're going to be interacting with up and running. So I believe I have a documents folder here with OSCP in it. The OSCP in my GitHub repository is a zip file because there is a DLL, I believe, that's required for it. So you can see I have these both in the same folder. I'm going to double click on the OSCP program, and you can see it is listening on port 1337. So the first thing that you should do is you need to figure out how the application works and how you're going to take advantage of it. Now, we know this is a vulnerable app and there is a buffer overflow that's available to us, but we still need to get some important information from this app. So what we're going to do is we're going to netcat to the IP address of my Windows machine on 1337, okay? We're going to hit enter, and it says, welcome to OSCP vulnerable server. Enter help for help. So we're going to type help. And you can see valid commands are overflow 1 through 10 and some value. So right off the bat, we know that whatever buffer we send over there is going to have to include this first command of overflow 1, overflow 2, overflow 3. We're going to be doing overflow 2. So every time we send over a buffer, it's going to have the prefix of overflow 2 and probably a space. Because if you look at the way that that's formatted, it's overflow 2 space and then whatever value. For the purposes of overflowing the application, we're literally going to be sending over a bunch of A's, capital A's. Now, if you don't know what a buffer overflow is, it means that somewhere in the program, there's a memory location that has a purpose. And the developer didn't do a good job of sanitizing any input to that memory location. And what we do is we send so much data to the memory location that we overflow the amount of space that was allocated to that memory location. So if it was 8 bytes and we send 16 bytes and the program accepts that, the program's not going to know what to do and it's going to crash. Okay? And then that's how we're going to take advantage of it, by figuring out where it crashes, telling the CPU where to go after the crash, and then executing our own code. So hopefully that's clear. So now that we know how this application works, we can type exit. Well, maybe not. I wonder why that didn't work. Exit. Okay, so we'll just hit Control-C. And we will go back and make sure our application's running. And it is. Okay. So the next thing we're going to do is we're going to close this window. And we are going to go to our folder that has these specific programs that I put here. Now, if we look at these programs, the first one is the fuzzer that I wrote this, but you could write one. Like I said, it's not a big deal. I just have this. If I wrote all of these programs in this video, it would be like 2 hours long. So you can use this fuzzer, or you can write your own fuzzer. It's not a big deal. This particular fuzzer takes arguments in the form of the IP, the port, and the prefix that we need to use. In our case, it's going to be OSCP overflow 2. Okay? And then you can see down here, it creates a new socket connection every time it sends a payload, and then it increases the payload in an incremental fashion until the program crashes. Okay? So what we're going to do is, the program is running, so we're going to open up a terminal. In the folder, we have this program. And we are going to run it against the program. So Python 3, fuzz, and if you look, the arguments are IP, which is the IP of the Windows box, the port that the application is listening on, which is 1337, and then the prefix that we know we need to send as part of the buffer, which is overflow 2. And basically what you do is you run it. Now you're going to want to run it more than once, because you want to make sure that it crashes around the same area, right? If you get one where it crashes at 500 bytes and one where it crashes at 2000 bytes, something's not right. You want it to be, if it's 500 bytes, maybe one time, maybe it's 520 the next time, maybe it's 480 the third time, then you know it's around the same area in memory where the program is crashing. So if I hover over my virtual machines, we can see this black box at the bottom that shows the application is running. Once I hit enter here, we start to send data. I'm going to come down here so you can actually see when the application crashes. Okay? So we're going to hit enter. It's going to start to fuzz the program, and then we're going to wait. And we're going to probably want to run this at least twice. If they're both in the same area, I would probably say twice is fine. 3 times would be ideal. If I was writing a buffer overflow, I might even run it 5 times, 10 times, just to make sure. Okay, it just crashed, and you can see it was right around 662 bytes. So what we're going to do is we're going to come back to our Windows machine, we're going to restart the application, and then we're going to come back to our Linux box. I'm going to clear the screen, and we're going to run the fuzzer again. And if it's around 600 and something bytes, then we probably are safe sending over maybe like 720 bytes and using that for the pattern to do the MSF pattern create. Okay, it looks like it crashed around 652 bytes. So honestly, between those two crashes, we could probably safely estimate that we could send over 700 bytes to MSF pattern create and be safe. You always want to send a bit more than the highest bytes that it crashed at. Okay, you want to have a little bit of a safety buffer in there. Okay, so what we're going to do is we're going to clear the screen. I'm going to run a command called msf pattern. msf pattern, and we want to do create. And we're going to send, we want to create about 700 bytes, okay? So that's what we're going to do. We're going to do this, and it's going to generate a pattern for us, okay? So now we want to take this pattern, and we want to send this over to the machine and make sure it crashes, okay? So let me just pull up some stuff here. And we're going to want to copy this. Oops. It's very early in the morning here still for me, so I'm not functioning at 100%. All right, so now that we have this pattern, what we're going to want to do is we are going to want to come over here to our test.py. And what we're going to do is we are going to, you should probably, if the least you can do is memorize without this buffer prefix, this is how you create a socket in Python. And a socket is nothing more than the combination of an IP address and a port used to connect to an application. So we're creating a socket called S here, and like I said, just memorize this, okay? Because you're going to type these two lines right here. You're going to probably put in every Python program you write that connects to something. You can see I have the IP here, I have the port, I'm creating the socket, and then I'm using the socket to connect to the IP and the port. The buffer is the data that we're sending over to the application. And you always, in Python 3, need to specify it as bytes. And you do that by prefixing this lowercase b in front of the string, okay? So right there we have the buffer of overflow 2, okay? So what we want to do now is we want to add to this buffer. We want to type buffer and then plus or equals. And this is essentially shorthand for buffer equals buffer plus. Okay, so we're just adding additional items to the buffer that already contains overflow 2. And what we're going to send over is bytes, and then we're going to paste this pattern in. Okay, and we're going to do that. Okay, now the next thing that I always like to add, because I've seen exploits without it, but I think it's good practice to do another buffer plus equals statement and add bytes, carriage return, line feed. Okay. And we'll see if we're looking good here. I think we are. And then essentially what we're doing is we're putting this buffer together, which now contains 3 items. It contains overflow 2, it contains this pattern, and it contains the carriage return and the line feed, okay? And I think we should be good. So let's see. Send buffer as closed. We're going to save test.py. We're going to come back to our Windows machine, and now we need to start Immunity Debugger, okay? So what we're going to do is we're going to double click on Immunity Debugger, and we want this CPU window to be the prominent window that's displayed. And now we want to come over and we want to restart our OSCP application. You can see it's running and it's listening for clients. So now the way that you interact with that program within the debugger is you go to File, Attach, and then you attach to the OSCP process. And you can see now all of this data that's here, okay? The registers, dumps, everything that you need to do this is here in these 4 windows, okay? And essentially you're going to be spending most of your time in this registers window and then this dump window when you're looking for bad characters, okay? Now here's the key. You can see down here it says paused. That means that although we have this application up and running, it is not currently working because it's paused within the debugger. What you need to do is click this little play button, Okay, now it says running. Okay, now we know the application is up and running and it's ready for us to send over our test payload with the pattern in it. So what we're going to do is we're going to go back to our Kali box. We're going to come over here and now we're going to run our test script. Python 3 test.py. Okay. And hopefully when we go back to the machine, we're going to see it in a pause state again in Immunity Debugger. So let's see what happened. And it's paused. So now what we are really interested in here is the EIP register, okay? You can see our ESP register. You can see all the pattern and the data that was sent over there. What we really are interested in here now is this EIP register. It says access violation while executing, and this is the memory address of the EIP. If you don't know what the EIP is, it's execution instruction pointer. I believe it's the register that tells the CPU what the next instruction to execute is. Okay. So what we're going to do is we're going to grab this EIP register address. So we're going to copy the selection to clipboard. We're going to come back to our Linux machine and we are going to run another program similar to pattern create, but this one is pattern offset. This is going to help us determine what the actual offset is or exactly where the program is crashing. Okay, so we're going to type msf pattern underscore offset. And we're going to paste in the memory address of the EIP pointer. And I think we're going to change this to 700. We don't need 720. 700. And then the other argument is the actual memory address of the EIP pointer, which we just grabbed from Immunity Debugger. So I'm going to paste that. And when we hit enter, hopefully it gives us an exact offset, which is what we're going to use to try and do the next step, which is to control the EIP, which means when the program crashes, we're going to put data that lands in the EIP and tells us, yes, we control this now and we can tell the CPU what to execute next. If we can control the EIP, which is like I said, the execute instruction pointer, we can tell the CPU, hey, this is the code that we want you to execute next. Forget about everything else. You do what we tell you here, okay? So when I hit enter, it gives us an exact match at offset 634. So that's important, okay? So I think what we're going to do now is we're going to migrate from this test.py. I'm going to open up what I have here, which is our exploit. And what we're going to do is we're going to start to build out this exploit now, okay? So now that we know the offset, we're going to add another variable here called offset. And we're going to put the value of 634 in here, okay? So what we need to do is now we need to basically build a buffer that contains some data that we're going to try and make land exactly in the EIP register so that we know we can control it. What I'm going to do there is I'm going to call another variable EIP, and what I'm going to make it equal to is bytes, and I'm going to make it 4 capital B's. So the capital B in hex is 42. So when we execute this code, what we would like to see is in the EIP register, if we can control it, is 42424242. Okay. So we have our offset, we have our EIP. Okay. So what we're going to do is we're going to start to assemble our buffer here. We're going to make it buffer equals, and what I've done is I've changed the overflow here to a variable called prefix, because from now on, that's what it is. We're going to be referring to that as the prefix. That is the overflow to command that the program expects before any other data. So what we're going to do is, as we build this buffer, we're going to start with the prefix, okay? We're going to add bytes bytes A, capital A, times the offset. So now we know the program crashes exactly at that offset of 634. We want to send basically 634 capital A's, okay? And then we want to add the EIP, okay? So now when we execute this, theoretically, when the program crashes, we should see in the EIP register 42424242. And if we do that and it is in fact there, we know we control the EIP and we can move on to the next step. Okay, so I'm going to save our exploit, and then I'm going to come back to Windows, and we see that our program is still in a pause state. The way that you restart it is you click the little rewind button here, you answer yes to the question. You can see we're back to our screen that we want to be at. The application is there, but we have to do something. We have to click the play button. So now it says the application is running, and if we look, we can see the application is in fact waiting for connections. So it's ready for us to send over our exploit. So what we're going to do is, I've saved this, we're going to go back here and we're going to do Python 3. And if I haven't done anything wrong, because like I said, we're writing this together, I should be able to just run exploit.py. It should crash the program, which would pause it in the Immunity Debugger. And if we go and look at the registers and see 42424242, we know we're in good shape. Okay, so I'm going to hit enter, and I'm going to go back to my program. We can see it's paused, so it's crashed. And if we come to the EIP register, it does in fact say 42424242 or 4 capital B's. So we know we do control the EIP register, and we can theoretically tell this program what to do next. Okay, so here's where it gets a little hairy. There's a couple of ways you can do this. You can do bad characters manually. You can do bad characters with Mona. I'm going to use Mona just because it's a little bit easier. But you can 100% do this part just by eye, okay? So now that we know what's going on here, what we need to do is we need to go back to our exploit program. We need to generate a string or a byte array of all of the hex characters from basically 1 to 255. 0 is always going to be a bad character. I mean, I've never heard of it being not a bad character. So X00 or 0 is always a bad character as far as these things go. Okay. So let's go back to our Kali box. And if I come back to this, I have a very easy program here. It's just a Python script that basically runs through 1 through 256 and creates a byte array of everything in hex. Okay, I got this. You could do ChatGPT. You could find it on the internet. You could write yourself. It's, it's a fairly straightforward thing. I'll show you exactly what it does. Okay, so if we go back to our window here and we do Python 3 and we do gen characters, you can see we have created a string of characters that starts at X01 and ends at XFF, which I believe is 255, okay? So now what we need to do is we need to add this to our exploit so that it runs after the program crashes and the EIP register is filled with the code that we control. And then the next thing that will be fed to this program will be this byte array. And we want to see how the byte array behaves in memory. And there are almost certainly going to be bad characters that need to be removed from the array that are going to cause issues with the exploit and the stability of the exploit. So we want to get those out. And we want to be able to identify those so that when you use msfvenom to generate your shellcode, you can feed the bad characters to msfvenom, and it will make sure that the shellcode does not include those bad characters. Okay, I hope that's clear. So we're going to do a couple things here. We're going to need to grab this pattern or this byte array. Okay, copy. we're going to need to go back to our exploit. And what we're going to do is I'm going to create a variable called all cars. Okay. We're going to make it equal to byte. And we're going to paste. And then we're going to do a colon, not a colon, a quote, and a closing parenthesis. So now we have all cars, okay? And I'm going to come down here, and after the EIP, what we're going to do is we're going to send all cars. Okay? If I could even type today, it would be wonderful. So I apologize. And I can not spell cars. Okay. So now the buffer consists of the prefix, 634 capital A's, the EIP, which is 4 B's, and all cars, which is this pattern, okay, that we generated, this byte array that contains all of the numbers in hex from 1 to 255, okay? And then we're going to send that over, and what we're going to do is we're going to use Mona to generate its own byte array and compare what's in memory and what Mona has in its byte array, and it will tell us if something looks incorrect. And I'll show you basically how to do it manually too if you want, if you chose to go that route. You're going to need Mona at least to get the jump ESP, but you could use Mona for this, and I found that it works pretty well. Okay, you just have to be careful and remove one character at a time, because if it tells you there's 5 bad characters, there may only be one. It may be that first character that's causing the rest to be bad. Okay, so let's save our exploit here, and let's make sure we didn't do anything wrong, because it's very easy to make a mistake here. We got the EIP, everything is in bytes. Okay, we're sending the buffer. So let's go back to Immunity Debugger. Let's rewind the application. Okay, let's press play. We can see the program is running. Let's make sure it's listening, and it is. So now we're going to come back to our Linux box. We're going to go back to our window, and we're going to run our exploit. So let's Python 3 exploit.py. Okay, and when we hit enter, hopefully the program is paused, which it is. Now we're going to use Mona to start to figure out bad characters. Now what you got to do for Mona to begin with is you have to set the working directory. And I will have all these commands for you in my GitHub repository, so you don't have to memorize all this stuff. But even if you just look online on how to use Mona to do this, there's probably 100 tutorials out there on how to do it. The first thing you need to do is set the working directory for Mona. So before I hit enter on this, what I'm going to do is I'm going to grab the ESP register, because we're going to need that, okay? So we're going to copy that selection to keyboard. And I'm going to actually paste it over here in my next Mona command, okay? So now that we've done that, we're going to hit enter on this Mona command to set the working directory. And we can see that that has been successfully done. Now I'm going to apologize in advance because the text with Mona is fairly small, but I'll try to do my best to explain everything. So now that we have the Mona working directory set up, what we want to do is we want to have Mona create a byte array, okay? And the way we're going to do that is with this command. It's a very simple command. All we're feeding it is the first bad character. If you remember, I said X00 is always a bad character. This is going to grow. Every time that we do this compare and we run this program and pull out a bad character, we're going to add any new bad characters that we find to this array, okay? So Mona's going to create a byte array with X00 removed from it, basically, okay? So we're going to hit enter, and hopefully it's going to work. And it did. It says 255 byte array written, and it should be ready for us to compare. Now, if you remember, I just grabbed that jump ESP, not jump ESP, the ESP register. And what we're going to do now is we're going to have Mona compare the byte array we just created with the memory in the jump in the ESP register dump and see if there's any bad characters, okay? And I'll show you how to do this manually after we run this command for the first time. So I'm going to paste this. This is the ESP register I just copied out of there after the program crashed, and we're going to hit enter. And it says possible bad characters here: 23, 24, 3C, 3D, 83, 84, BA, and BB. And I'm going to tell you right now, these are not all bad characters. The first thing that we have to worry about is this 23. And you can see that the one that is omitted already is 00. So what we're going to do is I'm going to minimize these windows. So we know we have to look at 23. Now, if you wanted to do this manually, the way you do that is you always want to go back to the CPU window. You go to the jump ESP, which is this window right here. And if we, let's see if I can get back. I don't know why I can't get back to where it shows that this is the jump ESP, because this is the memory address that we just copied. So what we want to do is we want to right click on that address and follow in the dump. And here is where we started to feed that byte array into memory. And you can see it's going quite well. 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F, 10, 11, 12. It's great up until we get to 22. The next one should be 23, and it's not. It's 0A, which means a 23 is probably a bad character, okay? So what we're going to do is we're going to rewind the program again. We're going to press play, okay? I'm going to add 23 to my next Mona command byte array that it creates. So I'm just going to do this over here in my notes on the side, just so I don't forget, 23. And what we're going to do is the program is running. We're going to come back to our exploit, and we're going to go to our byte array here that we created, and we're going to just get rid of 23. Okay, so you can see here we go from X22 to X24 now. Okay, so we're going to click save, and we're going to run the exploit again. And this is what you got to do for every bad character. Okay, so we come back over here, we run the exploit again, we go back to Windows, it's paused, we now have another address here, and we're going to grab that address. Okay, and we're going to copy that over to our Mona compare statement. You have to change that ESP register address every single time you crash the program, okay? So I'm going to paste that memory address there. And what we're going to do is now we're going to create another byte array, a new one, okay? And you're going to see I put my next bad character in there, which was 23. So now we have 00 and we have 23. So we're going to hit enter, and it created a new byte array. Now we have to do the compare again with the new jump, with the, I keep saying jump, with the new ESP register, okay, address. So we're going to paste that in here. This is the ESP register address I just copied, okay. We're going to hit enter. Now it says 0 and 23 are excluded, and possible bad characters are 3C, 3D, 83, 84, BA, and BB. So the next one we need to worry about is 3C, okay? I apologize for my voice. We're going to rewind the program again. We're going to press play, and our application is running, okay? So now the next one we need to get rid of in our program is 3C. So now we got to squint and we got to find 3C, which is right here, X3C. We're going to delete that. And now you can see we go from X3B to X3D. Okay, we're going to click save. Our application is running again. So now all we have to do is run the exploit again. Python exploit.py. All right, let's go back to Windows. We can see the application is paused. I have a new ESP register address here. I'm going to copy that. I'm going to paste that into my Mona command. And I'm going to add x3c to my byte array. And I'll show you this. I'm just doing it in my notes, and I'll show it to you when I'm pasting the command. Okay, so I think we're ready here. So now that we have the new ESP register address and we added x3c to our bad byte array, we're going to come over here and we're going to create another byte array with Mona paste. You can see now we have 00, x23, and x3c in the byte array. So it's going to omit those from the new byte array it creates. We hit enter. We're good to go. Now we run a Mona compare on memory versus the byte array again using the new ESP register I just copied. Okay, so we're going to paste that. This is the new ESP register I just copied. Okay, from when the program crashed. Going to hit enter. Okay, now we have possible bad characters 83, 84, BA, BB, and we can see 0, 23, and 3C are omitted. Okay. So the next character we need to focus on is 83. So what I'm going to do is I'm going to rewind the program again. I'm going to start running it. It's listening for connections. And now we need to get rid of 83. So if we go back to our Linux box and we go to our program, our exploit, we need to get rid of 23. So now we got to squint. 83, sorry, 83. I don't know why I was saying 23. We need to find 83, which is right here. So now we're going to back up, get rid of 83. So now you can see we go from x81, x82 to x84. I'm going to add x83 to my bad byte array Mona command. So x83. And we're going to run our exploit again. So we click save. Come back over here, we run exploit.py again. Hopefully the program has crashed. It has. We can close this. We're going to grab this ESP register. Again, paste that in our new Mona compare command. Okay, and now we can generate our new byte array with Mona. Copy. Paste, and you can see I've added x83, so now it's excluding 0, 23, 3C, and 83. Okay, so if we hit enter, our new byte array has been created, and now we're going to do our compare of memory versus the byte array using the new ESP register I just copied. Okay, this is a very repeatable process. Paste. You can see here's the new ESP register memory address that I just copied. So I'm going to hit enter. And now it says possible bad characters, BA and BB. So we're getting there. We got 0, 23, 3C, and 83 being omitted, and we have 2 bad characters possibly left. So now we have to get rid of, in our byte array, XBA. Okay? So we're going to rewind the program. We're going to click play. It's running. It's working. Okay, so now we need to get rid of XBA. So we're going to go back to our Linux box, we're going to go back to our exploit, and we're going to look for XBA, which is right here. Okay, so now we're going to back up. So now we go from XB9 to XBB. Okay, we're going to click save. I'm going to add this to my Mona command for the byte array, which is XBA. So we're ready to do our new byte array when we're back over on the machine. And we are going to make sure we save this, and we're going to run our exploit again. Okay, come back to our Windows machine, and we can see the program has crashed. It's paused, and what we're going to do is we're going to grab this ESP register, copy. I'm going to paste it here in my Mona command. And now we're going to do a new byte array with Mona. Same thing we've been doing. This is rinse and repeat. Copy. You can see now our bad character array consists of 0, 23, 3C, 83, and XBA. So we're going to hit enter. And Mona is going to create a new byte array with those characters missing. Okay. And now we're going to do a compare of memory with that byte array using the new ESP register I just copied. Paste. And we're going to hit enter. Okay, we're in good shape here. It says done. If you say here, comparing with memory at location, you have the stack. Hooray, normal shellcode, unmodified. So what we know is all of the bad characters that we need to give msfvenom now when we generate our shellcode, okay? So now what we need to do is we need to figure out the jump ESP, okay? But before we can do that, no, actually we can do that right now. We need our bad character array, which we already know, okay? And then we just basically need to run a Mona command that will to give us that information. I believe we can do it right now. Let me just grab the command, make sure our bad character array is updated. Let's see if we can just run this and see what happens. Paste. All right, so we have Mona, jump R, ESP, CPB, and then our bad character array. Let's just make sure that I got that. I didn't copy anything wrong. We hit enter. And okay, now we need to go to window. We need to go to log data. And we can see we have a bunch of memory pointers here, okay? So if we click on any of these, sometimes these will be protected. So you can see how the ASLR everything's false here. Like in real life programming, some of these may be protected, all of them may be protected, and then you're gonna have to change all of your tactics. These are all ways to protect memory. And you can see it's all false here. So theoretically, we could literally pick any of these. So what you do is you highlight it. I think you just double click on it. Yep. And it gives you the jump ESP right here. We can see that the jump ESP is this memory location. So now what we're going to need to do is copy that. Okay. So we're going to copy to clipboard. And now is when there's a concept called endianness. It's a little tricky, but it's not that hard, okay? What we're going to do is this memory address is theoretically in what's called big endian format. We need to convert it to little endian format, and don't worry about it. There is a website you can do this. It's very simple. I'll show you exactly what to do, okay? So we're going to go back to our Linux box. I think I have the website up for this. I do. So this site, which I will include in a link in the description below, basically will take big endian and convert it to little endian, okay? So what we're going to do is we're going to paste that memory address in there. And actually we have to get rid of this part. We just need the memory address. So that was the memory address that the Mona program gave us as the jump ESP. So we need to convert from big endian to little endian. So this is the new address that we need, okay? And we're going to actually call this in the program the jump ESP, okay? This is basically a pointer in memory. Just think of it as a pointer in memory telling the program where the shellcode is going to reside, okay? And there's a little bit more complexity around that. There's going to be these things called NOPs and a NOP sled. It's basically no instructions. It makes that memory space bigger because there's a lot of trickery within the CPU where everything is randomized to try and protect memory and all of that, and to protect against things just like this, actually. So we have our little endian memory address here. That is the jump at ESP. Now, when we do this in the program, we're going to have to modify this a tiny bit. Just make it hex, basically. So what we're going to do is we're going to copy this, and we're going to come over to our exploit. Okay? And we're going to add something here called jump underscore ESP. We're going to make that equal to bytes and we're going to paste that memory address there. But what we need to do is we need to make this in hex format. So x slash x slash x slash x. Okay, so that's our jump ESP. That's extremely important. What we can get rid of now is this. We don't need this EIP anymore. And we're not going to need this all characters anymore because we're going to be feeding this shellcode now. Now, the next thing that we need is something called NOPS, or no operations, or a no operations sled. It's really kind of complicated, but the CPU does like this randomization of the memory in the stack, okay? And that randomization is random and it's difficult to predict. So what an attacker does is it puts a NOP sled in a big range of memory. And if the program jumps anywhere into that sled, it just executes the remaining NOPs, does nothing, and will run the payload that's next to the sled. Okay, so basically we're putting a bunch of, hey, don't do anything in memory, and at the end of that we're going to tack on our shellcode. Okay, I hope it's very complicated. I can't even imagine what it's like to try to do 64-bit exploits, but it is what it is. And NOPs are dependent on architecture. And x86 architecture NOP instructions are typically the equivalent of x90 in hex. And this is a 32-bit memory space, obviously, so I'm going to send over 16. And I think if you do that, you'll be fine. If you're having trouble understanding this, just know you need to add NOPs. And if you're on x86 architecture, just add 16 of them. Okay, so we're going to do NOPs equals... we're going to make this equal to byte x, and you remember I said it was x90, right? And we're going to do that 16 times, like I said, because this is a 32-bit memory, 32-bit address space, okay? So right now we have our prefix, we have our offset, we have our jump ESP in little endian format, and I made a mistake there. See, this is why you always want to make sure you check stuff. I forgot a quotation. Then we have our NOPs, and everything's in bytes, obviously, times 16. Okay. Now we are ready to actually generate shellcode. This is the fun part. Okay. We can get rid of this all cars. And what we're going to do is we're going to actually generate some shellcode. Okay. So we're going to go to our window here, and we're going to use msfvenom for this. You can generate shellcode, and what you're going to need is it's just like if you're using msfvenom for an exploit, except that the format that we're sending this over in is in it's basically in shellcode for Python. Okay, you can do it for C, you can do it for a lot of languages. We're going to be doing it in Python. So I'm going to copy this msfvenom statement over here, and I'll explain it. It's pretty much like any other msfvenom statement. We're doing a Windows reverse shell, my machine, my port, okay? This is why sometimes when you have exploits that you download from GitHub, they don't work because they contain shellcode that's hard-coded with these values. So if these values are different for you, that's not going to work. So you would theoretically just generate new shellcode and pop that shellcode into the exploit, and it should work. So we have our local host, our local port, exit function thread, just include it. And then here are B for bad characters. This is our bad character array. And then we want it in the format of Python, okay? It's going to be different if you generated C shellcode. It'll look completely different if you generate Python shellcode, okay? So we're going to hit enter. And hopefully it's going to generate our shellcode. And it does. So now what we need to do is we need to grab everything from buff to the last quotation mark. And this is essentially the instructions to basically connect to our reverse shell in shellcode. Copy. We're going to go back to our exploit, and we're going to paste that in there. Okay, so we have our buffer, our buff equals, and it's all in byte format. You can see that, so that's all good. So right now, if we look at our exploit so far, we have the prefix, the offset, the jump ESP, the NOPS times 16, the shellcode. So now what we want to do is we want to type shellcode equals buff. So basically we're taking the contents of buff, which is essentially adding a line of shellcode to buff every time this runs. So now buff contains this entirety of this shellcode. So now we're just naming it shellcode to make it a little easier to understand for humans, right? So we have shellcode equals buff. Now we need to assemble our buffer. So we're going to back out and we're going to get rid of some of these spaces. The prefix is going to stay the same, right? We're still going to send 634 A's over, okay, to crash the program. So we got A times 634. What we need to do now is we need to get rid of EIP because we don't need that, and we don't need all cars, right? Because we changed this now. What we need to do is feed it the jump ESP, which is the location in memory where this code is all going to execute, right? So now we're feeding it the jump ESP. Then we have to feed it the NOPS, which is the no operations, basically to expand the size of that memory that we have the ability to run this code in, okay? So we're just going to put our NOPS here, and then we're going to say after you do all these no operations or do nothing, generate the shell code at the end of these NOPS, or run the shell code at the end of these NOPS, okay? So we're going to add the shell code. So now our buffer consists of the prefix, 634 A's, the jump ESP address, which is basically telling the EIP or the instruction pointer where to go in memory. We're going to do a whole bunch of nothing with this NOPS sled to make that memory space bigger. And then we're going to use the shell code. We're going to run the shell code next. Okay? So this is where it gets exciting, boys and girls. Theoretically, we're done here, okay? We should be able to run this program, and we should be able to get a reverse shell, okay? So that's exactly what we're going to try. I'm going to save this exploit, and if we didn't make any mistakes, we should be able to do this, okay? So if you remember, our msfvenom statement used port 4444. So before I forget, I'm going to open up a netcat listener, an LVP, and we'll do 44444, okay? And then we're going to come back to our Windows machine. We're going to rewind the program again, okay? And we're going to press play, and we're going to come over here and look, and we're going to see it's waiting for client connections. So now, theoretically, knock on wood, next time I run this exploit, we should go back to our listener, and we should have a shell, okay? So let's see, boys and girls, if we did everything right, it's very exciting, okay? So what we're going to do is we're going to close this msfvenom, and we're going to go back to our window we've been running our exploits in. We're going to click clear, and now we're going to run our exploit again and see what happens, okay? We're going to hit enter, and let's go and see what happened. Let's first check. Uh-oh, the program is still running. That is not a good sign. So let's see if we did something wrong. I'm going to guess we don't have a shell. We do have a shell. So there you go. Look at this. Who am I? Yeah, that makes sense because if the program crashed, then we wouldn't be able to connect to it. So unbelievable. It worked the first time we did this. I was expecting us to have to modify something, but there we go. Now for a bonus, what we're going to do is I'm going to exit here. I'm going to show you how you can write the exploit to pop a shell in the same window, okay? It's really not that hard. So we're going to go back to our application, and we're going to rewind again because the application is unstable, obviously, because we just essentially overflowed it. We did. So you can see it's paused. I'd hit rewind. Let's hit rewind again just to make sure. Okay, and we're going to press play. So now the application is running again. So what we're going to do, and this is a lot easier than you would think to do this. We don't need this window anymore because we're going to be popping a shell in the same window. We're going to come back to our exploit. There's a couple of more things that you need to import here, one of which is time. So we're going to import time. And then I think we have to import a Python library called subprocess, which allows you, it's not theoretically like multi-threaded, it's multi-process. So you can run a subprocess, and you need to be able to run more than one process because, you know, if a program is just executing one process, obviously we can't start a listener and then run the rest of the program because the listener is taking up the process. So we have to create a subprocess for that listener. Okay, so the way that we do this is actually pretty straightforward. We're going to come down here, and we're going to enter this. We're going to call our listener something really creative. Listener, okay, and we're going to call subprocess popen, which is where the magic happens here. Popen is going to open this subprocess and allow us to execute essentially two things at once, a listener and the exploit. Now, just to be fully transparent here, you know, this could cause problems, right? I mean, the tried and true way to do this is open a listener in another window and run the exploit. This could introduce problems, but in this case, it doesn't. It works quite well, actually, and I think it's pretty cool when you can pop the shell in the same window. So we're going to do a open parentheses and then the bracket, and then the command we're going to execute is netcat, and then the arguments we're going to give it are nlvp, comma, and then we're going to feed it the port. So obviously we hard-coded 444 in here. So I mean, we're just going to basically, and it's got to be a string, and 4444 is not a string, so this should work. Let's see. Netcat nlvp string port. I just want to make sure I'm not making any mistakes here for you guys. So string port. So then we need a closing bracket, and then we need a closing parentheses. All right. So we have listener, subprocess, popen, and I'm not using an actual IDE, so it's a little bit more tricky. But we have our bracket. I just want to make sure I did this right. Netcat nlvp string 44444. Okay, that looks good. And then really all we need to do is have the listener wait. That's it. Oh, you know what? I forgot. There is something else we have to do. I think we imported time because we really should give a slight delay in the program so that there's not some kind of race condition where the listener is still trying to establish a connection and the exploit is already done. So what we're going to do is we're going to do time dot sleep, and we'll sleep for 2 seconds. That should give, I think that will give the listener enough time to connect or establish. And then really all we need to do is have the listener wait for the connection. So if we come down past close, we just type listener dot wait. That should be it. All right, we'll know soon enough. Okay, we'll click save on our exploit, and then just make sure our application is running, and it looks like it is. And then what we'll do is we'll come back to our box, and we'll run the exploit again, and this time it should pop the shell immediately in this window after the 2 second delay, obviously. So we're going to hit exploit. It says listening on 4444, and bam, we got our shell. So That's how you basically write a 32-bit exploit. There's several steps you have to follow. The first is you have to fuzz the app, okay? And that's going to help you determine around where the program is going to crash. Then you need to generate a pattern and test for offset, okay? And you're going to do that with MSF pattern create and MSF pattern offset. That should give you the exact offset after you run the offset part of the MSF pattern with the EIP after the program crashes, okay? After that, you need to verify you have the EIP. We did that with 4 capital Bs, and when we saw that the EIP was 42424242, we knew we were good to go. Once you control the EIP, then you need to generate a byte array with all of the characters from 1 to 255 in hex. You send that over to the program after you crash it, and then you examine the dump of memory in the ESP register using Mona and compare each time you pull out a bad character that Mona gives you, you build your byte array, bad character byte array, by comparing it to the dump of the memory in the ESP register. And once you have all of those removed, Mona will tell you everything looks good. You can generate your shellcode and then build out your program so that you can give the shellcode into the program after you crash it, theoretically, or overflow it. Crash it is a bad word. Overflow it. And it will execute your shellcode and give you a reverse shell. This is really kind of complicated. I know they took this out of the OSCP, but I wish they hadn't, because I kind of found this to be kind of an interesting topic. And I'm hoping that this helps you and that it helps me to maybe eventually write some 64-bit exploits, buffer overflow exploits. Now, buffer overflow exploits in 64 architecture is a whole different animal. And you're going to need to use tools like IDA Pro or something like that, because Immunity Debugger is not going to work. But this is good practice. You should definitely learn how to do this in 32-bit architecture, x86, before you try and venture off into something more complicated. So I hope this video helped you. I hope you learned something. If I used any links, they'll be in the description below. If you have any questions, comments, concerns, criticism, just want to say hi, drop a comment, check out our Discord server. We'd love to have you. All the information's on my YouTube page. I want to thank you for watching and bearing with me in this long video, but this is a pretty complicated topic. I hope it helped you, and I want to thank you for watching, and I'll see you in the next one.